I mentioned in the previous class, we spend a lot of time thinking of the algorithms for machine learning, but not worry too much about where the data is obtained from, right? Most of the papers use benchmark data sets, but if you now go to solve a practical problem, most of the time, you don't have a data set to begin with, right? So the issues of how to collect data in an intelligent way, as well as reduce our reliance on data, has been some of the very recent works, especially in the context of deep learning. This is very critical, right? And if you recall, we covered these different strategies from simple data augmentation, where you make small perturbations or simple perturbations on your data to prevent overfitting and hopefully get better generalization. So in a way, multiplying your each sample to many more samples through perturbation, right? And this one is mostly random as opposed to the robust setting we saw in the previous lectures, where it was the worst case perturbation. And then we said there are other settings where if you only have not just the labeled data, but also unlabeled data, how do you combine the two? And we'll see that in the upcoming lectures on how to do that well. As well as issues of transfer learning and domain adaptation, where you already have a pre-trained model and you're now transferring it to a new task or even a new domain. Right, those are ways to handle it. And then what we were focusing on was active learning, where given a task, given the domain of unlabeled samples, how do you strategically decide what to label? Right, and here we saw there were mainly three setups. The most common is the pool-based sampling, where the pool of unlabeled samples is fixed. And then you're taking these mini batches of samples that need to be labeled. And so it's the algorithm, the machine learning model is using this active learning algorithm to decide what mini batch of samples should be selected for new labeling. And we then saw the stream-based was when it was the samples in a stream. So once you decide not to choose a sample for labeling, you lose it, right? You can't go back and take it later on. So, and then the hardest we were discussing was synthesizing samples. So it's not just this fixed set of unlabeled samples, right? But you're free to synthesize different samples. So there could be different setups, right? There could be one where you're asking the annotator to come up with a sample, or the model itself is synthesizing the sample using some generative frameworks or simulator-based frameworks, and then showing the annotator or the human whether this makes sense, right? Whether this has the properties of the given category or given task you're after. So this is the hardest, and there is very little work done here, right? So if you're interested in open problems in active learning, I think this would be a very important area to think about. And we discussed how you could get exponentially more efficiency in the synthesis setting as opposed to the pool-based setting, right? Because if you have the ability to synthesize good samples, then you can really learn your classifier in a much better way. But it's also much harder to do, so most of the time we'll limit to the pool-based setting. So any questions here? And then we said within pool-based setting, what are the main design parameters, right? The most important is this acquisition function, because this is telling us how do we decide the criterion to acquire new labeled samples. So this is the most important one. And then the other ones are more kind of practical considerations. So how many queries or the size of this mini batch you want to send to the human annotator for labeling, right? How many do you select at once for labeling? Because ideally you want to do it just one by one, right? Because that way you can be most efficient in the number of samples. So you select each sample, go retrain the model, decide now based on this new sample how the result changed, and only look at acquisition function based on the new model. But the downside is, first of all, this is computationally inefficient. You have to keep retraining for each new sample. And also the latency, right? You're like, it takes, if it's like an experiment that takes time to happen and you're only doing one at a time, it could take a long time for your model to get to a good accuracy. So in practice, you would this is mostly limited by the bottleneck of the oracle. So how many human annotators you have or how many experimental equipments you have, that's usually the limitation because you're not doing it online, right? So you kind of stop your machine learning algorithm, let the offline data labeling happen, then come back and then think about retraining the network. And that's where the next consideration comes up, whether you should just retrain from scratch or you should use your existing model and try to fine-tune it or update that model. Right? So here you have to be careful because two things can happen. Right? So if you focus too much on just the new samples, right, you keep using your new samples and keep updating to many, many epochs, then you may forget the old ones. On the other hand, if you just train for a few epochs, you may just not move from your old model, right? So this is why it has to be this kind of fine balance that you somehow have this mix of old and new samples, and you keep training, but also ensure that there is good changes from your previous model. So I think in practice, this is the most delicate, and almost there's no theory here, right? Because, this kind of deals with the adaptive sampling issue, and here actually the distribution has changed. Right? Like there's an old distribution of samples, and now this active learning is completely destroying the IID assumption. So you're having these new samples that dependent on the old ones, right? Because the old samples train the previous model that decided the new samples. And so this makes it delicate to analyze.
So here, this fine-tuning doesn't mean that, for example, you would take a pre-trained model or ImageNet, but want to apply it to
No. There's no, and that's even harder issues, right? So we're not looking at transfer learning. You have your pre-trained model from the previous set of samples.
Previous set. Okay.
Yeah. And so in theory, if you go back to the classical theory on active learning, there you assume you just completely retrain your model from fresh, right? You take all your samples, the old and new, and train the best possible model with that. Whereas when we saw the generalization theory and all this, right, much of the classical ones may not apply to deep learning, and so you're not going to want to retrain from scratch anyway, both from the issue of computational complexity, but also it may not really yield good gains, right? So it's not clear. And so this issue of what it does to generalization, how you want to do this well, is still open. And in fact, a more general form of this is like this lifelong learning or this never-ending learning, right? So in most of the settings we've looked at so far is the stationary setting, meaning there's some fixed distribution, you keep getting new samples from it, so ultimately you want that to converge. Whereas if the distribution itself is changing, then you don't want convergence, right? You want to keep always adapting. And in those settings as well, you don't want to completely forget the past, but you don't want to also just remain in the past, right? And that fine balance is it's application dependent. There should be hyperparameters on how to tune that. But also we don't have a good way to specify what is that balance that's needed. So in the general setting, it's very hard because it's not even clear what you want to go after, right? But in this specific setting, let's assume these are still all samples from the same fixed distribution, but now you're collecting them in a non-IID fashion, right? So now it's still a very delicate matter on how you want to mix the old and new samples.
Could this apply in a non-stationary setting, or is this exponentially more difficult when we can assume non-stationarity?
So the non-stationarity, even without active learning, is hard, right? What is the most general non-stationary setting? You're assuming that all your past samples can affect the future samples, right? So in that case, this very long-term dependence. So in the general case, we don't really even know what to do, right? And then people use these POM-DP models, right, partially observed Markov decision processes, to have a way to think about limiting the dimensionality of the hidden state, right? So there's only in some fixed dimension you can evolve through this hidden variable, and so there's still some limited complexity in your world. So that I would say is a very general framework to deal with those. Again, there are different kinds of non-stationarity there, right? So there you could say this hidden state is evolving, and hence, and as I'm taking the action, I'm changing this distribution. But there could also be non-stationarity in the parameters of that model itself, right? That's another level. So there's not one notion of non-stationarity, right? There are different notions here. And so in this active learning case, it's perhaps one of the simplest forms. If we assume it's still the same fixed distribution, but the way we are collecting samples is in a non-IID fashion. And so there is, still some of the theory can go through. I will not give the details, but so here you can still analyze. And especially it's like a martingale argument if you, used martingales, or the main idea is like kind of conditioned on, what matters is only the current model, right, in making those future decisions. So everything, all the information from the past samples is summarized into your current model. And so through that bottleneck, you're deciding the future samples. So, in all of this bottleneck is the way to go about, because you have like a fixed way to propagate dependence from the past to the future. So I'm not covering those details, but I think that's kind of, there's still, I think, interesting open problems, especially in this setting where you're incrementally training your model on what's the right adaptive sampling to do there, right? Because there should be like an optimal scheme of how to mix the old and new samples. And then, this last one, I'll come to that in the end. But is the overview of active learning clear? And then we said we'll first focus on the acquisition function, because that's really one of the important design considerations, right? And we said the intuition is you can be optimal in the number of samples, in terms of how many minimum number of samples you need to get to a level of accuracy if you go by selecting the least confident samples, right, or the most uncertain samples. And that makes intuitive sense that you put your budget on the most uncertain samples, because that's when your model tends to get it wrong, so you'd rather ask the human answers for those samples. And then this is where we got into the details, where we said what is the right notion of uncertainty, right? So we said if it's the standard softmax classifier, right, you can think of the value of the softmax, right? Like, so this, you're looking at the y hat would be like the soft outputs, and then you're asking what is the sample with the least confidence. And so when you're looking at the max, you're only looking at the top softmax output, right? And then we said the maximum entropy was a kind of, it was considering all the categories, not just the top category, and so it could be much more informative, at least in the information theoretic sense, on where the most uncertainty is. So if you just had your frequentist setting with your softmax classifier, this is all you could get at, right? So you can't get more. And then the idea was maybe we should look at Bayesian frameworks as well for having a better notion of uncertainty. And this is where we distinguish two kinds of uncertainties, right? The aleatoric and the epistemic. And I think this distinction is fundamental, right? This is very important when you want to think of using machine learning in many practical problems, right? Because you will have all these different sources of noise. There is measurement noise coming from the sensors. There is just inherent hidden aspect, right? You just can't measure everything through your samples. So what's hidden and what's really the uncertainty due to limited data, we want to distinguish the two. So this aleatoric was this inherent uncertainty, right? So even if you had infinite samples, you couldn't overcome that. So that's something inherent. Whereas epistemic that's arising from limited data. And I think this figure, made that very clear, because these blue points are these training data. You're only observing this curve in some regions, and so there is epistemic uncertainty in the other regions, right, where this training data is not available. Whereas the aleatoric uncertainty is just throughout everywhere. Right? I mean, it could very well depend on the data and the region, or it could be even just uniform, right? So that's kind of the two forms, the homoscedastic and the heteroscedastic. But the important thing is to be able to distinguish the epistemic uncertainty from the aleatoric. And what we discussed was, if you look at the standard softmax classifier, it does not incorporate the epistemic uncertainty very well. Right? So meaning it doesn't know that it doesn't know. These are called unknown problems, because here it should have realized that I really can't make a good judgment, right? But it doesn't by itself, unless you make further changes, get to that. And so this is also known as a miscalibration, because it's not correctly calibrated on its confidence level. Right, and we saw that in this curve as well. This curve here is from the standard neural network, and you can see the black were the training samples, and even when there are no training samples available at the extremities, it's still pretty confident, and we don't want that, right? So, and so this is where it can have blind spots, right? So what would be the danger of using this notion of softmax confidence measure for active learning? So you would decide that, oh, I'm very certain here and there, so we're just not sampling from those regions. So you could miss entire regions where your classifier is really bad, but you're not even asking the annotator for verification, right? So you could just be having really bad performance in big regions of your sample space. And in high dimensions, you can't go and brute force measure in all sample spaces, right? So that's why it's important to have a good measure of uncertainty. Is that clear? And then we were discussing how to get lightweight Bayesian neural network, right? So, the Bayesian notion is having the prior and then given the data, updating the posterior. And so, we should really be sampling from the posterior in the true sense of a Bayesian inference, rather than just having a point estimate, right? Because that really captures both the uncertainty and your estimation process, and being able to give the best possible answer. But that's too expensive, and then we were looking at these computationally efficient mechanisms. So I was hoping to breeze through it, but since there isn't a dedicated course for Bayesian inference here, at least not one that's happened over the last year, I thought I'll spend a bit more time today on variational inference. But before that, the very simple kind of notion was to not do this full-fledged Bayesian inference, but just kind of think of dropout as a simple data-independent way to have an ensemble of networks, right? So if you're now looking at dropping out activations with some independent probability, then you are not having just one network, but many networks, right? So every configuration of the nodes is a valid neural network, and what you're really looking at a mixture of these, an exponential number of neural networks. And so it has a lot more capacity than just the base network. And so this is more expressive, but it can also incorporate uncertainty better, right? And then we said that you can sample now multiple times from this network, and then you can assess how much they agree. And the intuition was if the neural network didn't have a lot of samples, such as in these regions, when you sample from this, it's not going to be robust. So you're going to get different answers. So with this disagreement, you should lower your confidence. And so that was the dropout method. But a somewhat more sophisticated method was looking at putting a prior distribution on the weights and then trying to approximate the posterior, right? So this is more data dependent rather than dropout, which is data independent. So you hope you'll get a better measure of uncertainty with this. And so here the idea is now each, instead of coming up with point estimates of your weights without a prior distribution, you can now look at having some prior on the weights and then looking at the posterior, and then based on the posterior, you can come up with an estimator.
How are the priors generally chosen?
Mostly for computational efficiency, right? So that's what we'll come to. I mean, in the ideal world, you want it to be some, prior information of your domain or your data, but I mean, the computation is such a big bottleneck that even the simplest, we'll see in the next slide, simplest priors and simplest setting, we still don't know how to do it at a reasonable scale. At the scale of any of these modern, big enough deep learning networks on ImageNet, right? We don't have a working Bayesian neural network at scale, at that level. So that's kind of so far off that, we haven't really thought about what's the best one. Whereas in classical statistics, people have thought about this. There's the notion of informative prior and the non-informative prior, because the other option is to say, maybe I want my prior to be really non-informative in a way that I'm more robust, right? Like, what's the worst case prior you can think of? And so there are people thinking about that. So there's a lot of literature in classical statistics, but in deep learning, we are still taking very baby steps to get this to work at scale.
Yeah, but also because, these priors in Gaussian post-regression also that actually are giving good uncertainty quantification. I mean, the reason they're doing that is because they are far from uninformative.
Yeah.
But because really they're encoding something we assume. And so without encoding something reasonable about our data, how can we hope that the uncertainty calibration that these posteriors give us have anything to do with
so that's
the true process?
I mean, then it's data dependent, right? If you have a reasonable number of samples, then you're not only dependent on the prior. So in the asymptotic, when you have an infinite number of samples, you completely discard the prior.
Yeah, but
right.
Intuitively, for example, in the Gaussian process setting, in the setting where I don't have, for example, any samples in a certain region of space, then really what allows me to make to estimate the uncertainty there is really just the prior, right?
Mm-hmm.
So, and if that is the thing we want to remedy using these Bayesian networks, I don't see how we can do this unless we choose our prior in a particular.
I mean, we're not saying we will get the exact right level of uncertainty, right? But we will at least make sure it's uncertain enough. Whereas in the standard, like, frequentist setting, without if you don't make modifications, you will think it's certain, right? So at least it's avoiding that extreme case of like being certain when you shouldn't be.
Okay.
Right? Doesn't mean we may have the right measure of uncertainty. It's more like most of the time we want a confidence bound, right? We think that this is like the bounds on confidence, not the exact confidence curve.
Yeah, it just seems, because in these very high dimension examples, basically it just seems that it's very easy to sort of go wrong with the prior that it puts.
Yeah, and most of the time it is wrong, right? So it's very rare, even classical settings, to get the right informative priors. But the goal of the prior then is to, ensure, again, this is now a hyperparameter of what variance you set or what bandwidth in the kernel, right? So those will determine what happens in regions where there's almost no data, right? But at least you're getting some base level uncertainty there, right? So you're not going to end up with this bad setting where it's certain, right? That you're ensuring that won't happen. And then given more data, you're going to be you're going to shape keep your uncertainty better, right? You're going to be modeling the true distribution better. Does that make sense?
Yeah, I mean, I guess like that's a more quantitative thing. I'm still not fully sure. But yeah, in principle, I understand. Yeah.
Yeah, I mean, the quantitative thing will depend on the specific case, right? How many samples you have, how informative is the prior.
Yeah, I guess so. Basically, so what I was thinking, like in the Gaussian process setting, oftentimes one doesn't go too much wrong with some kind of smoothness prior. I mean, that's because we assume that the data has been presented in geometrically meaningful ways.
Yeah.
So any smoothness prior will give us something that's not too off. And that is the thing that I don't see immediately. If I put priors now on the weights of the neural network that are interacting in this very complicated nonlinear way, I don't see why I should have the same confidence that even some sort of roughly smoother like prior or so will do something reasonable.
I mean, because what you hope is, kind of a similar smoothness arguments, right? If the weights, even if you're like in a, kind of with some confidence bound you perturb, right? Like it should still kind of hopefully yield similar results, right? That's what you hope for.
Well,
right?
basic stability, another way to do stability analysis with respect to the weights.
Exactly, right? And that's what this disagreement is measuring, right? So where you have a lot of confidence, then you are robust there. But if you haven't seen enough samples, then you're going to disagree, and that's when you should be less confident.
Is that in the Gaussian process case? Can one also see just putting a prior stability analysis on the weights, or is it because basically if I have a region where I don't have anything, and then I perturb my data points away from this region? I mean, this will not necessarily lead to a drastic change of the
yes,
results.
But that's what, right? That's why there's some base level of uncertainty, right? So that's where you're setting that you should at least have some level of uncertainty where there's no data to begin with.
Okay.
So then, at least you will output that I don't have enough confidence here.
Okay.
Right, and especially for active learning, that's crucial, right? Because then you can go and collect data in those regions. It doesn't claim that it's the right level of uncertainty there, but you hope that some bound is correct. Yeah, so that's the main motivation. And so in a way, the dropout can give you some level of uncertainty, right? But it's since it's completely independent of data, kind of the data is not shaping the posterior, right? So it's not as accurate as it would be in where you had a prior and came up with a posterior distribution. And so that's the motivation to go to the weight uncertainty. But indeed, you see here the computation jumps, right? Because here it's like linear, right? Just the number of units, like you're sampling, you can just sample. You can just do like draws of each unit and then draw as many samples you want. But here, there are quadratic number of weights, right, if it's fully connected. And so now you have to go and sample many more. So if it's like the number of computations kind of grew by an order of dimension. So this is very expensive, right, to actually go and sample. So we are not gonna, and to compute the posterior, then to sample from it is very expensive. So we are not gonna do the exact posterior estimation, we're gonna do approximate, right? But I guess this slide was just contrasting the frequentist maximum likelihood with the Bayesian map estimator, right? So in the Bayesian case, you come up with a posterior. If you still want only a point estimate from the Bayesian inference, the standard one is the map estimator or the maximum a posteriori, right? It kind of makes sense. You want to look at the mode of the posterior distribution. And so that's kind of the idea is you're additionally incorporating a prior, which wasn't the case in your frequentist setting.
So the left-hand side is the usual network.
Yes. More generally, it's the frequentist, it's the Bayesian, right? So in the usual network, you don't have any stochasticity. It's all deterministic operations, right? So it's whereas here now you can incorporate a prior on the weights. Okay, so as I said, Of course, in the ideal world with infinite computation, we'd be just all Bayesians, right? But that is a big a requirement, right? As I said, scale is almost the only thing that matters right now for putting this in practice. And so, variational approximation is again a pretty old, it's a classical set of techniques, and there's been a lot of push in the recent years to modernize it to deep learning. So we'll see some of the tricks, it's going to be like 1 or 2 slides, so it's not all the details, but at least I hope you get the high level idea of how in practice we do these approximations. So the first step is to come up with a variational distribution. So what that means is instead of the exact posterior, I'm going to look at an approximation to it, right? I'll find another distribution Q that's close to P of W given D. D is the data, W are the weights, right? So that makes sense. I mean, it's very hard to come up with an exact form of the posterior. I'll instead find an approximate distribution from which hopefully I can sample much more efficiently. Right? If you go back to the dropout that was super efficient to sample, that was independent of data, right? That was just independent on the activations. So we can come up with all those kind of constraints here, right? For instance, I could make the Q to be just independent on the weights. So the general posterior distribution is going to be dependent, right? Like all the weights in the networks, like these potentially billion parameters are dependent. There's just no way I can sample. But instead, I'll approximate it with a distribution that's independent on the weights. And I could also look at some very special parametric forms. I could say Q should be like Gaussian or exponential, something simple enough that I can easily sample from. And then the question is, how do I find the optimal Q? Right, so within some class. So usually I'll make it parametric, but I should still find what is that optimal theta. Right, so that's the variational approximation. And like Kullback-Leibler distance makes sense in a statistical sense, but not so much in robustness. So there's all these recent works with Wasserstein distance and optimal, generally synchron. So don't think of this as also like set in stone, right? This is what classically people have done, but there's also more recent push towards making this more robust, but still scalable. But that's not a direction we'll deal with a lot in this course, but think of this as there could be other means to look at measures between distributions. But Kullback-Leibler is the most standard one. So okay, I can write down this objective, but again, can I come up with efficient ways to optimize this, right? So, it's going to be expensive, of course, to do exact optimization. Instead, I'm going to just do local search, right? So I can take gradients, but while taking gradients, I can switch the expectation and the gradient step. Because this is nothing but, Kullback-Leibler, if you recall, is the expectation of the log of the ratio of the densities, right? That's the Kullback-Leibler formula. I hope everybody remembers that. If you have two distributions here, let's say P and Q, right? Ignore that notation. This is just so what you have is expectation over distribution P of log of P by Q, right? So that's the definition. So you can write the Kullback-Leibler in terms of an expectation. So and this is anyway a general statement, right? Like in general, if you have any expectation over a distribution, if you assume continuity, you can switch the, and I guess also differentiability, you can switch the derivative and the expectation steps. And so that's a standard trick that's done to, again, make this more efficient, because you can't hope to compute the exact expectation and then optimize over this. Right, so yeah, so now the question is, Okay, and this is more just the chain rule, right? So this is like not, I think this, once you look at this is obvious, right? So this is just change of variables. So, okay, we have this form, and now the question is, how do I choose like the space of distributions for Q that's simple enough and tractable enough even with all these modifications? Any questions here?
So here theta should be dependent on the data set D. Because
No, yes, the answer will be dependent, right? Theta star will be,
because QP is something dependent on data.
yes,
And Q should be approximate of.
yes.
So here, originally we should have a D in the Q amplifier here.
No, theta star will be a dependent on D, right? But not the, but the idea is, it's still efficient to sample. Like your sampling mechanism doesn't change depending on D, right? Hopefully, at least.
Yeah.
It depends on how you
So
have the
single
space of
way.
distribution. Whereas in the posterior form, the dependence on D could be arbitrary, right? So that's when it's, and the example was, even if you started with an independent prior on the weights, once you have the data, the posterior could, make everything dependent. So okay, we made these approximations. Now the question is, which one do we choose? And it's natural to start with Gaussians, right? So sampling Gaussians is tractable, it's easy, and also make them independent across the weights. So this is now much cheaper than doing any dependent distribution. So as I said, this is a good starting point, and there's just, I guess, one detail here. So again, this just doesn't work. This, instead of sigma for the standard deviation or sigma square for the variance, instead we're parameterizing it with rho and epsilon, and that's to ensure that if you recall, log of 1 plus exponential is still always positive. So like you take derivatives, you move, it's still positive. So just a simple trick, right? So that's the only reason, right? Because if you now directly try to take gradients and you make the variance negative, that's vacuous, right? So instead of trying to project it to the positive side, you just, it's more convenient to do it this way. So I guess that's the only detail, but other than that, we are just using this previous notion, right? So we're going to take these local steps or the gradients and take expectations over them. So we're going to take some set of samples and try to approximate those expectations and update the parameters. Right, so the steps I've written down are just specific to the Gaussian distribution. You would have the update of the mean and the variance terms, and that would just follow the change of variable rule I showed in the previous slide. So there isn't any additional detail than what I wrote before. Right, but it's just making that step by step for the Gaussian distribution. Right? It's still expensive because you have to sample all these, for each weight you have to now draw multiple samples, right? And there are like a large number of weights in the biggest networks, potentially up to 1 billion set of weights. So, many times people just try to have a subset of weights be having a Gaussian prior rather than all of them. One of the standard tricks is to do it only in the last layer or last few layers, because that's when you want your measure of uncertainty to be kind of using the stochasticity there, right? It matters more at that point than the previous layers. So if you only have limited computation, you want to put your stochasticity in those last layers. And there is a lot of evidence that even those lightweight networks can give you much more benefit compared to the standard ones. But this is a general notion. So any question in the general variational framework, because I know there hasn't been many other opportunities to think about this, so I want to, even if it's not directly related to active learning, I'm happy to answer that. Okay, so given that we have this notion of variational approximation, you can do this. This plot on the left is obtained by this what they call the Bayesian base by backprop model, right, with the weight uncertainty. And so you can see that it's kind of, at least in this toy example, giving you a much better notion of uncertainty, right, that it is able to capture the epistemic uncertainty much better than this frequentist model. And so the question is, so these are different possibilities for the acquisition function. So I'll show you some example results of using active learning in these different domains and see what are the lessons we learned. So it'll be more empirical from this point on. So one of the things we did, I was personally involved, was this task of named entity recognition, where you want to go to a piece of text and say whether something is an entity and then classify what is the type of that entity, right? So the idea is there's some special structures within your text document, right, like a person or a location that's more important, right? This is really the crucial information in the document that you want to extract. So this task makes a lot of sense, but this is also really expensive annotation. As you can see, if a human has to go read through this entire block of text and correctly figure out these so many different categories, right? So it is time consuming. And so one question we asked was, can you reduce the number of label samples required and still get a good NER model? So that's the reference for details. So here there's actually one more kind of additional detail, right? Here you're taking a sequence of tokens. So token is typically at the word level. So now you have a sequence of words and you want to classify all of them. Right, so it's not just now, so it's more sequence tagging rather than just one, classifying one token. And so since you have the sequence, you can ask, how can I think of confidence bounds for a sequence? And so one option is to think of some normalized measures. You could just look at the joint probability, that's one option, right? The other is to try to normalize it. If you have now variable length, so in language you have not all sentences be the same length. Right, so now you want to account for that, because otherwise if you're only going for the least confident, the longest sentences will be the least confident, right? But that's not clear, that's the optimal way to do active sampling or active learning. And so instead you could normalize it. That's just a simple detail, but could be useful for sequence tagging tasks. And same with the Bayesian case, you could look at normalized measures or just the joint measure on the sequences. And so these are some of the results. So the main thing is the lesson learned, right? So at least, so this was onto notes. This is the largest open data set for NER, about I think 625,000 words available, or tokens available, right? And so what we see is, right, you just need very small percentage of samples to get the state-of-the-art accuracy, right? So which is, I think, one thing that's important to also use this as a way to evaluate different data sets, right? Because people are advertising data sets based on the size, right? I have this many million samples, but no one is questioning what is really the true diversity of these data sets. Right? Because especially so many of them are just collected straight from the web. I mean, if you just take all the Reddit text, you want to ask, okay, is this really diverse? It's debatable, right? So, I mean, that's what at least the latest language model has been trained. I don't know if you've been following the OpenAI language model and the controversy behind that. That's a tangential one, but that was trained from Reddit comments. There's, of course, the bigger societal questions as well, if we should be really mirroring Reddit comments. But my comment was more in connection to diversity of the data, right? If you're just blindly taking your data set from some online source, so much of it could be redundant. So we shouldn't just be going by the size of the data, but have ways to measure the true diversity. And this could be one surrogate measure, right? I mean, this is not directly measuring some kind of entropy, but in a way, it's kind of indirectly related to that. So you could, say that if you can do it with only a subset of the data, then this data set is not truly diverse. So I think that's one lesson we can learn from these experiments. And the other was here, if you're, in this example, so the MNLP, if you remember, was just the normalized for the length, but it's just the least confidence estimator, right? So it's the standard softmax. And in this case, and the bald was the Bayesian one, in this case, we couldn't see a very big difference, right? The curves are truly just overlapping one another. But you will just wait for a minute. I'll show you other experiments where it does make a difference. So the other lesson is not to just go by one domain or one set of experiments to make a judgment of which algorithm is better, right? So you need much kind of more comprehensive ones to sometimes glean out why one algorithm could be better than the other. So that's the other lesson. And I think the third one was this, normalizing for the length seemed to make a difference, especially in the beginning. If you have a budget of very few samples, then normalizing for the length makes sense, right? And in there, I guess you really care about the budget. So, if you only have a limited number of words to optimize over, you shouldn't just go by these long sentences. You should really kind of look for all the sentences, right? And that, again, make intuitive sense. And the other was also looking at the best shallow model, right? So let's say we gave the shallow model the full set of data, right? So we are giving it all the advantage it can have, right? Giving it all the data, and then asking, if you can now do deep learning instead, but with limited data collected in an active way, which one would be better? Right? Because what's really one of the remaining arguments for shallow models in domains like text, right? So one argument is if I have limited data, then maybe deep learning is not the appropriate thing to do. I should go for shallow models because they have fewer parameters, right? But on the other hand, if you have the ability to collect it in an interactive way, you don't collect all your data to begin with, but instead collect it in an active learning fashion, you really don't need a lot of data even in the deep learning system, right? So, and that's, I guess, kind of the takeaway that, if we currently don't have well-architected active learning systems, right? At least not many examples of that. AWS recently released one where there is an ability to do active learning, but it's still kind of is offline and requires you to go to Mechanical Turk, right? Like wait for the examples and do this. So it's not as seamless as just having all the data and then iterating over different models to come up with the answers. But say in an ideal world, if we made active learning very seamless, you should really be doing it that way, right? So you should never collect your data beforehand. You should try to optimize on how best to collect your data. So that's kind of the main takeaways, right? That uncertainty sampling seems to work well here, right? And if you have the ability to do active learning, deep learning is not sample heavy, right? Or data requirements are still low.
Sorry, going back real quick, what is the RAND line?
Oh, just random sampling.
Okay, and that was able to get up to 85?
Yeah, but took much, I guess, longer, right? So, I mean, it makes a big difference, especially if you have a small percentage of your data. I mean, because at 25%, you see it already reached, I guess in English, it was 25%. I mean, that already reached state of the art, whereas random was somewhere hovering, below the state of the art, right? So like 25 was somewhere here, So it took much longer to get to that final percent. And also, I guess this kind of is saying, I mean, if you're collecting this passively, it's much more of a diminishing returns, right? To improve the last few points of a percent takes so many more samples. But if you're doing it actively, it's much faster. And that's the other benefit of active learning, because you're being much more strategic. Whereas if you've already gotten to a fairly good accuracy, right, if you're just passively sampling, it's very hard to improve that because most of the samples are going to be not informative. Right, so that's the main takeaway from this work, that uncertainty sampling seems to work well, and just the least confidence softmax based confidence bound is enough, right? And we can do with much fewer samples, right? But this is where we don't want to stop here, right? It's in this idealized setting where we had all the ground truth and we could try out these different schemes, we could get this really promising result. So this is like the best case, right? But the reality is going to stop us from achieving this best case. So what are some of like the things that are still open? So we'll come to that in a minute, but before that, I think we can think of other forms of active learning before I address the further questions I just asked. I forgot the sequence was slightly switched. Yeah, so the next topic will be now asking, can we further optimize our budget? Right, so depending on the task, right now we said let's go and look for the most strategic samples. But many times you're not just asking a human one simple question, right? It's some really composite question that you're asking them to do, right? In the case of like image classification, for instance, you want them to go and like label some fine-grained categorization, right? So ImageNet is 1,000 categories. It's not going to be this drop-down menu of like just select one of them, right? So you can't just go and select one of the 1,000 categories. So instead, there's a hierarchy, right? So in the case of ImageNet, it was the WordNet hierarchy over which you're constructing that and then asking the human these binary questions, right? So in that setting, if you have this hierarchical structure, you should be making use of that. So you can be active not just in terms of the samples you select, but also the questions you select. And this makes sense if you're interacting between two humans, right? If you want to gather further information, you're going to change your questions based on what answers you get, right? So you're going to update what you're going to ask, and that's what we wanted to ask in this second work, which is to do active learning when there's only partial feedback. So instead of asking the finest category to the human annotator, you can just ask anywhere, right? You can just ask, for instance, is this a dog or not, instead of the specific breed of the dog. So you can decide what to ask. And you can just kind of keep moving on. You can say, okay, on this sample, I only have this coarse-grained label. I don't have the fine-grained label. And maybe the fine-grained also requires an expert and maybe more expensive, right? So you could look into all those considerations when you're doing active learning. And so that's why we call partial feedback, because during your training time, you don't necessarily have the full information on each sample, right? The fully required label information, but something partial. So how do you train on that? And we looked at it in the case of hierarchical categorization, where we said, we can now decide on each sample at what level of the hierarchy should I ask my question, right? So there are two parts. One is actively selecting the sample. Given my current model, I can go and decide what is the best sample to select next, right? But then I can also say, given the sample, what is the best question I can ask? And so that's an additional, aspect we are being active about. Right? And so the idea is, again, there's a notion of uncertainty, right? Maybe you're pretty certain that it's a mammal, so you don't need to ask that. You can then directly go to fine-grained question, because if you're sure at the coarse-grained level, you just skip that question, you just directly go to the fine-grained. Right? But maybe in the beginning you still want the coarse grain, because that will help you at least get these high-level classes well. So the algorithm can kind of figure out where the most uncertainty is and then try to optimize. And so now the details are in terms of what are the ways you can decide where in the hierarchy you want to ask. Right, so you could like think of different, so now there are some fixed locations in the hierarchy, right? So these are all the locations in the hierarchy where I can ask the question, and you can look at different measures. One is this expected information gain, right? So you can look at how much entropy got reduced because I'm going to ask this question, right? So in expectation, what do you expect the information gain to be? And so that's a natural measure. You could also make it kind of more just a high-level information, right? You could just look at how many of the potential classes decrease, meaning if I'm very high up here, the number of potential classes is all these leaves, right? So that's a large number of classes. But if the more I'm further down towards the leaf, I have only few potential classes. So in this case, I'm really focusing on drilling down to the finest category as quickly as possible, right? Without worrying about the overall uncertainty of the model. So I could use that. And the remaining classes is a similar measure, right? So they're related. So in our experiments, this remaining classes perform the best, although I guess going in, there's no real reason why that should have been the case. I mean, they're all very related, right? So I guess the main takeaway here is really kind of looking at the setting. The one extreme setting is where both you're selecting the data actively and also these questions actively, and the other is completely passive where you're just uniformly sampling your data and uniformly sampling your binary questions. And you can get quite a bit of gain by doing this actively, right? So the main takeaway is to think about what you can be strategic about, right? One part was being strategic about which data points to label. The other part is being strategic about what questions to ask. And the other is you don't need to get the full answer, right? So given only partial label or partial feedback, you can keep training once you have the structure, so you're making use of the structure to keep training on partial information. So that's kind of the takeaway, and you can do this in so many other settings. Any questions here? Right, so these are some forms of active learning. Now we'll try to ask, okay, these worked great on these data sets, right? But taking that to the real world involves so many more steps. So as I said before, these are the best case results, right? So some way this is the best case result because, there could be many other constraints that will stop us from achieving this. So what are some of those constraints, right? So how did we arrive at these results? So as with any other machine learning problem, there are going to be hyperparameters, right? So here we chose the best possible hyperparameters for every setting, right? But in the real world, you can't do that. You just collected your data with some choice of hyperparameters. You can't go back and collect more data with additional hyperparameters, right? I mean, that means you're spending more, right? You can't choose between the different hyperparameters, and that's a challenge, right? So you can't go this and do this retrospectively declare a winner. And so the question is, if you doing this without this kind of proverbial crystal ball, how do you get active learning to work well, right? Because in the real setting, this is all, you went ahead, made a decision to collect a sample, you already paid the price for it. You can't go back on those decisions. So if we now do this, so this is where my collaborator, Zach Lipton, worked with a student, Aditya, where he did quite an extensive sweep of hyperparameters and looking at what performs the best where you just don't have this hindsight, right? So you're just setting hyperparameters, collecting your data, and does active learning still work well? And here's where this Bayesian model turned out to be much better than the frequentist one. And so, because I was telling you before that this epistemic uncertainty is not well modeled by the softmax classifier, we shouldn't be using this. But on a single data set where you had the luxury of all this different hyperparameter tuning, and you could go back and retrospectively declare the winner, that didn't emerge, right? Because for some choice of hyperparameters, it still worked well. On the other hand, if you didn't have that luxury, the Bayesian one is more robust because it's kind of having a better measure of where truly the uncertain regions are. And so it's performing better, right? So that's kind of the moral of the story, is you do want to do much more extensive studies before sometimes a true winner emerges, right? And so in this case, having the Bayesian neural network made a difference. Okay, I mean, you can look at the details in the paper, but that's kind of the takeaway, right? So this was that was the crystal ball one. So there's a more general case where I think this is still an open problem. That's why I've even written, though you're not supposed to see that I needed to get more info. I just wanted to check if there are some even more recent work than a few months ago when this came up, right? So you feel free to go and check if there are follow-ups. That was my to-do, which I forgot. But the question is this, right? In many cases, if you're not collecting your data for a particular task, right, you're just collecting your data, then you may want to use it in different tasks or different objectives. That's when active learning could become very problematic, right? Because how you're acquiring new data points is based on this particular architecture, particular task, right? So now if you want to transfer it to a different model, different task, you could be much more in trouble. And there it does seem to happen, right? So you should only be doing active learning if you are certain this is the task I really want to solve, right? Like you should be, and in some cases this makes total sense. If you are doing drug discovery, yes, I mean, it's for a particular cancer I'm really going after, right? I mean, it could have other beneficial uses in different diseases. That's more, people are not really optimizing for that to begin with. So there it makes sense because all your money and time you're spending on this task. But in other setups, it's not so clear. You're collecting this text for named entity recognition. Maybe you're going to use that for, I don't know, knowledge-based construction. You could use that for sentiments, right? So the same annotations could be useful in other ways, right? So then it's less clear, right? And especially if your named entity recognition, you change the categories of entities, right? You're saying now, I only want some subset of entities, I don't care about the others, right? Even in that simple change, it could have now a drastic impact on the performance because the active learning was really optimizing for the given loss function, the given problem specification. So that's what I think there's an open problem right now if you're doing active learning, but in somewhat of a task agnostic manner, right? It can't be completely disconnected from the task because then, you could have that, but then that's only trying to make the data as diverse as possible, right? So you're going to say, it's more like a coverage problem. I have some sample space, try to collect the most representative points. And there's been work, especially if there are submodularity structures in your sample space, you can do this. It's called it's like an extension of k-means, right? Here, instead of the centers being the means, it's actual data point, right? So you're looking at some representative data points. So people have done that notion of representativeness to collect data, right? So then you're going and strategically collecting only these representative points. But it's not clear. I mean, that's too few, right? So that's so what's kind of the right balance of both this representativeness and fitting to a particular task, that's unclear. So that's another open direction to think about. Any questions here? So yeah, so that's, yeah, so you want to choose active learning based on what your requirements are. First, you should have the ability to do active learning, right? So you should be able to go collect now this limited set of samples, come back, train, and go back, right? Not always you can do that. Then the second one is what acquisition functions to choose, and preferably you should be doing some sort of a Bayesian neural network which can give you a better sense of epistemic uncertainty, right? But there are computational bottlenecks, so that's where you have to balance that. And the third one was ensuring transferability if you're not certain that your data will be used only on this particular task, right? These are some high-level considerations to think about, right? And there are still a few other issues related to this, right? I mean, so far, I think, why is this overfitting happening, right? So we said if you try to now transfer over tasks, it's going to be pretty bad performance. That's because, if you look at this in the lens of general interactive learning, right, which includes bandits and reinforcement learning more generally, this form of uncertainty sampling is only doing exploitation. There is no exploration, right? Because it's looking at the results of the current model and looking at the most uncertain, right? So that's exploitation. So there's no exploration component, and this overfitting stems from that issue, right? And so now you can ask, if you truly want to keep some exploration part, are bandits or more general reinforcement learning the right ways to think of the problem, right? Because then the exploration ensures you're still exploring your sample space, and so at least in the beginning you have enough kind of data points from different parts of the sample space, and then towards the end you can more specialize towards your task and exploit, right? So that could give you kind of this good balance between diversity or representativeness and task-specific performance. And people have started thinking about this, but I wouldn't call it in the most kind of visionary way, if that's what we use, right? Because people are trying to use reinforcement learning to try to learn the best acquisition function, right? But there, if you're not really, if you're still optimizing on this particular task, you're not going to get that benefit of exploration, right? So you should kind of then do it in a meta-learning sense, in the sense you should look at multiple tasks or look at transferability, right? So, and our reinforcement learning by itself is going to be very data heavy, right? So if your whole goal is to come up with a data efficient scheme, you're first spending a lot of data to try to learn this, right? So these are all some of the challenges. So that's why it's still a very delicate issue. There's certainly no final answer to these questions. Any questions generally about active learning? Yeah.
I'm not quite sure whether I understand what you mean by get correct at first, because I think you mentioned it, right?
The hyperparameters, right? So how did we demonstrate those results? So in those results, we looked at different schemes, right? And we chose the best hyperparameters for each of the schemes. And then we declared the winner, right? So for each hyperparameter run, it was a different set of samples.
Yeah, that's right.
But in practice, we can't do that, right? Because that means we are spending so much of our data budget. And so a more realistic setup was where it's like, it's like looking at some set of data, deciding hyperparameters, and then, you're staying with those hyperparameters, right? I mean, anytime you're choosing new hyperparameters, you can only do it within this limited data. Right? We are not giving you the luxury to try out different hyperparameter runs and then declare the winner.
Yeah, but for example, at first we only have a certain data set, right?
Yeah.
So can we make it wrong? Because we can only fit this to...
Yeah, that's what you choose, whatever, that's why, right? How do you choose that hyperparameter is a detail, right? You have to, but whatever the choice, right, you can only do it based on that limited data, right? You cannot go back and say, oh, once I looked at this best hyperparameter, this choice of data was wrong or not suboptimal, right? Or it was suboptimal. Like you're stuck with your choice, you're stuck with your data you've collected so far, and you can decide hyperparameters only based on the data you've collected so far. So this is more realistic, right? In that case, that was like, and that's why Zach calls it the crystal ball, because somebody was telling you, this is the best possible hyperparameter. Now fix this and go and do active learning, right? That's not going to happen in practice. Any other questions? Yeah, so in the last 15 minutes, I want to talk about some other issues around data, right? So I think yesterday you mentioned about the annotation noise, right? In fact, this is so common in practical settings, and even some of the benchmark data sets, there is a lot of annotation noise, right? Because most of these are obtained by crowd workers, right? So one is, of course, we are paying them very little amount of money to do this, right? So it's almost unethical to expect extremely good samples. There's so many societal and ethical issues concerned with that, right? But the other is the way these even interfaces are, right? Some of the interfaces used for labeling can be very problematic. I think we talked about the ImageNet interface a few weeks ago in the generalization lecture, where if you recall, it was like a screen with many, many images, and you just go and pick like what you think are the positive and the negative examples, right? So then people are going for the most obvious or the quick example, right, and may miss out the harder or the more nuanced examples. So it's not learning a true model of all possible instances of a category. And so there are issues of just the labeler not having enough attention or making random errors. Then there are the issues of bias due to the annotation interface itself, right? And then there are issues of how we combine these results, right? Because now typically there is not a single annotator, because we know it's going to be noisy. Now there are multiple ones. And so in this work, what we looked at was when there are multiple annotators, how do we reconcile their results, right? And the standard setup is each sample in parallel, you're having multiple annotators annotate them. And this is expensive, right? Sometimes it's as many as 20 annotators per sample. You could have had a data set that's 20x bigger, right, if you could just get away with a single annotation. And so the question is, can we get away with just single annotation, but instead try to learn a model across all the examples on what the noise is, and try to kind of use statistical means to correct for that noise, right, or incorporate that noise. So that's what this work looks at. And kind of that's the idea, right? In the standard setting, you just do majority rule. So before the machine learning model even sees the samples, we are removing information on what the different annotators are thinking, right? So that's why for robustness, you hope you have multiple annotators, then you provide the majority vote to the machine learning model. But now the question is, if you gave all this raw information to the model, can it do better? By the way, also as an aside, one of the practical considerations, when I was talking to people on convincing them to use active learning in many of the practical, very, very large-scale, production setups in industry, right? What they told me was when they used active learning, right? So they're going on for these uncertainty sampling, right? The most common outcome was that these samples just ended up being wrong. So you think you're very uncertain on this image, it's just an annotator made a mistake, right? So active learning really wasn't useful. In fact, it would have been dangerous to automate this, right? If you blindly just now did active learning, you're now training on wrong examples, right? So that's why in a practical setting, it's so dangerous to just put these methods blindly. Right, you need extensive setting. And so once there is this issue of label noise, then active learning is in fact the wrong thing to do, at least the uncertainty sampling. because the most uncertain will be the wrong ones. Sure, you're now helping correct this, right? So if your goal is to now go to the human annotator, correct it, it's still useful, but maybe it's not the best use of resources. Right, so there is still, by the way, an open area of like how to incorporate both label noise and do active learning simultaneously. Right, this is not, now it's actually a different objective, right? You don't want to just look at the confidence error rather the least confidence by itself, because the annotator could have also made an error. Right, so you kind of almost want to reason, is this error because the model is making the error or an annotator is making an error? Right, so let's say in the ideal world you have a good model of what errors annotators make and what errors model makes. Right, you further want to decouple those two errors. Right. So that's why it's beneficial then to have now a good model for annotator errors, right? Or at least start incorporating. Like start now saying each sample, I can expect it to be noisy due to the annotator. So in addition to the inherent stochasticity in my label process, there's an additional noise due to the annotator. And so this is now further decomposing our errors, right? So, the uncertainty quantification field really tries to, that's why classify different errors and tries to have separate measures for each errors, right? So we can learn a lot from that field and bring more of that to deep learning, because we need a better, transparent understanding of where the errors are coming from. So that's kind of the high-level comment, and now kind of diving into what we can do in terms of this data annotation process and incorporate the label noise, right? A simple model is to kind of look at a data-independent flip of labels, right? Obviously this is not true in practice. Maybe, what sample is, right? Like there's some, will really fool the annotator, right? So that's a harder noise. So in the beginning, we'll ignore that and say like just the annotator randomly is just sometimes clicking, right? They're just so tired or inattentive, so they kind of like are doing this random noise. So that's a good starting point, and that's what we assumed in this work. But you can extend on that, right? And so now you have this confusion matrices you want to estimate across all the samples, because now this is an average over all the samples, right? Because they're going to make this error on each sample. So you can go ahead and estimate the confusion matrices. So the confusion matrix is what's the probability this annotator will flip a category to another category, right? So it's that matrix. And if, say, I had the true measure of this confusion matrix, I could just do a weighted loss minimization, right? So now I can go take all the samples. Let's say this annotator, I was having very less confusion. I'm going to weigh his samples more compared to another annotator where the confidence was much lower, right? So I'm going to downweight. I'm going to just up and downweight the samples. So that's softer than just the majority, right? It's like really incorporating the error that each annotator is making. And it will also distinguish the experts in one category from the amateurs, right? Because one person could be very good at dog breeds but not cat breeds. So, in that part of the, that set of categories in the confusion, based on the confusion matrix measure, you can upweight your samples, right? So it's also able to do that. So the core of this work is how to estimate these confusion matrices, and then use that in an online fashion or an iterative fashion because you want to estimate both your machine learning model but also your confusion matrices. So you want to go back and forth between them. So I'll just show this kind of iterative process, right? So the main important thing is, right, so you come up with a model of your different annotators, like how in this binary classification it's just how noisy they are, right? And you use that to do a weighted loss minimization, and then you train your machine learning model. So using weighted loss objective, you train your machine learning model, right? But now how do you update your annotation quality. I mean, you don't have these confusion matrices to begin with. You have to train it with only the given data, right? And this is where you can use your trained machine learning model as a surrogate for the ground truth, right? Because what is the ideal scenario, right? So when this has converged, you want your machine learning model to be close to the ground truth, right? So you're kind of driving it, hoping that you're driving it towards that setup, right? Because once you have the ground truth, then you can estimate your confusion matrices. So instead, in these intermediate iterations, you're using the machine learning model to ask for disagreement, right? Because what the majority rule is doing the disagreement at the each sample level, right? So it's just doing sample by sample, whereas the machine learning model is aggregating all the information across all the samples in a weighted way, and then looking at how each annotator is disagreeing with this model. So it's in a way much more globally aggregating information of disagreement, right? So and the other benefit is you don't need multiple annotators for each example. So as long as you have the identity of annotators across different examples, right, you can still use that to update the confusion matrices and update the disagreements, right? So that's the benefit of using this intermediate step of estimating confusion matrices and using the current machine learning model to query for the disagreement. Is that clear? So that's kind of what the setup was, right? And I won't give all the details, but the main thing is you can prove in theory that if you have a fixed budget, as long as your annotators are fairly accurate, right? I'll come to the details of what fairly accurate means. And as long as your model has good capacity, right? So that means that there is, you're selecting a good function class where it's possible to get good accuracy. Then your generalization error is minimized by having just single annotation per sample. So that means you're better off annotating more examples rather than putting all your budget into annotating one example using many annotators. And that makes intuitive sense, right? Because we are now having this global estimation of confusion matrices as a way to try to incorporate label noise. So, and for generalization, you're better off getting more examples, right? Because that's giving you fresh information. And that's what we actually found in practice as well. And so this is again a downside of the way the data sets are collected, because most of the open data sets no longer have the raw information of what the annotator said. Right? They're already pre-filtered. It's only the majority rule that you see with further secret sauce that goes into coming up with the final results. Right? So that's another, I think, lesson to be learned, that if you're constructing a new data set, please keep all the information on how you constructed the data set. Right? So I think because then you can really benefit not just from trying to minimize the cost of annotation, but also looking at the bias, because now you can go through these trained confusion matrices, you can go and look at disagreement, right? You can do post hoc analysis on existing data sets if we had this information. And through that, maybe you can come up with these bad or wrongly labeled examples. Right? But so many times we just don't have this information, and that's problematic. And so those are some takeaways from this work that,
Is this kind of result, is this general for all sorts of predictors or just specific classes of predictors?
In this case, it was just general, right? So we were kind of doing the standard, complexity argument, like VC dimension, like argument, right, or Rademacher. But yeah, I mean, this is assuming that your model has essentially enough capacity to model this, right? And that makes sense, because if you had really a bad classifier, right, there is no hope that that will help you improve the confusion matrices. So the idea is, if your annotators are not that bad to begin with, right? So the starting model assumes everybody is fully accurate. That's how you train your machine learning model in the first iteration. That model is reasonably accurate, right? And then they're helping improve each other. And so again, this is only a bound for theory. In practice, you can go to much lower accuracy. And in this setting, we assumed everybody was the same quality, but you can now allow different qualities, right? It's also interesting where you don't have the wisdom of the crowd set up, but more the stupidity of the crowd. Let's say there was one expert and a lot of amateurs who made random errors. In our setup, that would work. It would still work out, because if those errors are mostly random and there is a consistent answer given by a few experts, right, then the confusion matrices kind of mirror that, right? So you can kind of incorporate that information better, whereas that's completely lost in a majority voting setting. You had a...
So by single annotation, you mean just one worker labeling
one,
each sample?
yes.
Is it possible that that's then overfitting to whatever latent subjective biases this one annotator has? Because I can see how more workers adds more noise because of that random aspect, but we might be misled into fitting to that annotator's beliefs.
I mean, that's why we are estimating those beliefs, right? We are estimating the confusion matrices, and we are weighing our loss based on that. So if this worker tends to make a lot of error, I'm going to put less weight on him, right? I mean, and this is a passive setting, by the way. We are not adaptively saying, what should I go and only choose these annotators who are better, right? So you could then play that game as well. But here we are just assuming we'll just let the annotators label in a random way, right? So I'm just randomly allocating my samples to annotators. So I know their identities, I know who labeled what. I can go back and update the confusion matrices.
Okay, so I guess I just don't fully understand. So this confusion matrix is updated, and then once it's fully updated, you then choose the best annotation from a single.
We are not currently doing that, right? So that's the next step. Right now, it's already, you've chosen the annotators, right? You've allocated the annotators to your samples. You have these annotations, so it's the passive setting. This is not an active setting. And now you want to say, how do I best use that information? And in this budget optimization case, we are just saying, out of all possible allocations, what's the best allocation I can make? Yeah.
One thing, so intuitively I would have, I was a bit surprised that there's no mention, so even if the quality of the annotators becomes worse and worse, this bound still holds?
No. This bound assumes this. They're fairly accurate. And I was saying an extension is when, an extension is where there are some workers that are fairly noisy. In fact, the majority could be fairly noisy, but these few experts are really good experts, right? And that noise is fairly random. You can still hope for this result to hold.
Oh, I see.
That's an extension, but not, what's written there. Yeah. Yeah, so that's the takeaway from this part, right? So that was a different topic, I won't cover that. Saying that you want to incorporate the noise in the labeling process and try to again find now estimation mechanisms to overcome that rather than kind of say it doesn't exist, or try to use a highly redundant and a costly measure like a majority vote. So that's, yeah. Great. See you tomorrow again. Thanks for making it. I appreciate it.